Move to the last unit of your course on electronic circuits. Last day we have discussed about the feedback amplifiers, and hopefully you remember this kind of architecture: the feed network and back network. You have like in the feed network the corresponding the gain function is given by A, and in the back network the gain function is given by B. Okay. And you understand that there is a kind of negative feedback, so the signal that is getting coupled over here, if I call this signal as S of F, then based on this S of F and S of I, which is actually the input signal, so the signal that is ultimately received by this feed network is given by S of E, that is equal to S of I minus S of F, or S of epsilon is given by S of I minus S of F. And typically, the output signal, this S of O or S output can be written as A by 1 plus AB times input. So, in other words, the gain is given by A by 1 plus AB. So, you are well versed with this particular topology, as we have already studied the feedback. So, last time while we discussed feedback, so that time both this feed network and this back network, they were insensitive to the frequency. So therefore, what we expect that the amplifier circuit which is present over there, so the amplifier is supposed to provide same gain irrespective of the frequency. So if you have some capacitor, so sometimes we have observed that the capacitor is acting as a short circuit whenever we consider the coupling capacitor kind of thing. And sometimes the capacitor was acting as an open circuit whenever there was a bypass capacitor kind of thing, right? In fact, effectively the impact of the capacitor was not seen in the amplifier design, right? In the A part. Similarly, in the B part, if you can remember, what we have essentially in the B part, essentially what we have is simply registers, right? Either one register or more than one register. So as this B part, this back network, essentially since it is comprised of resistances, so therefore this is insensitive to the frequency, right? So therefore the basic difference between the feedback circuits that you have already studied and the oscillator circuit is that the difference is that this time last time what we have, this A network and the B network, the feed network and the back network, both of them were insensitive to the frequency, right? They are insensitive to the frequency. And this time what we observed that both of them, that is A network as well as the B network, they have these networks this time they are sensitive to the frequency. So you must be having some frequency sensitive elements in the amplifier design. In the amplifier part, obviously there were some frequency sensitive elements, like we have the capacitors, right? But those capacitors were made inactive. If I have the coupling capacitor in series, these capacitors, they are considered to be a short circuit. If I have the bypass capacitor in shunt path, in parallel path, we assume that under certain frequency these bypass capacitors were assumed to be open circuit. Eventually, the effect of the capacitors was not present, and moreover, in the B network, in the back network, there was no such frequency sensitive elements. But this time, what we have, this time, this feed network and the back network, both of them, they are frequency sensitive this time. So what I can write, so since there is a function of frequency, so what I can write, this the gain function in the feed network can be represented as A of S, and the gain function in the back network can be represented as B of S. Okay, and therefore the output signal S of O, that can be, since this entire thing is a function of frequency, so therefore O of S is given by AS upon 1 plus AS BS times SIS. As you already know, this is the typical expression for the feedback network, A by 1 plus AB, where A is the gain of the feed network and B is the gain of the back network. So from that I can conclude, I can simply compute the gain with feedback, that is given by AFS is equal to AS by 1 plus AS BS. So that is the thing that we have already, so you can only this expression, I think this expression is familiar to you. A of F is equal to A by 1 plus AB. So that is the only thing that we are getting from the feedback expression. Now what happens now, this entire thing 1 plus AB, if you can remember, this 1 plus AB, this is known as the desensitivity factor, 1 plus AB. Now this time this L of A, so this time we have provided one particular name to this ASBS. This basically this signifies the loop gain, because whenever the signal is present over here, then whenever it passes through this AS path, it experiences some gain given by A of S, and then the same signal is also traversing through this BS. So whenever the signal is traversing through this path, the loop gain is given by ASBS. So sometimes this ASBS is also known as the loop gain. So I can write this L of S is equal to ASBS. Okay. Now if you closely observe this expression, AFS is equal to AS by 1 plus ASBS. Now suppose, for example, what happens to the circuit, or what happens to the output if your ASBS, that is the loop gain, is equal to -1. Suppose ASBS becomes -1 for some given frequency, not for all frequency, but for some given frequency. Suppose ASBS, this product, is becoming -1. Then what do you expect? So mathematically, what do you feel? If ASBS approaching -1, that means A of Fs is approaching towards infinity. So what is A of Fs? This is nothing but this output signal by the input signal, SOS by SIS. This is SFS. And when this LS or ASBS is equal to -1 for some given frequency, then what happens is A of Fs is becoming infinity. A of Fs approaches to very large value. Suppose it is approaching towards -1, then A of Fs approaching towards very large value. What does it mean? That means, or it is very large, that means even for no input, essentially for no input, you can have some given output. Even if SIS is equal to 0, you can have some SOS, non-zero SOS, right? So some non-zero output signal you can have out of this circuit. That means what? Essentially you don't have any SIS. Essentially you don't have any SI. Still you'll be able to have some non-zero SOS if this condition holds good. That means this ASBS, this loop gain, the product of this feed network gain and the back network gain, if this product approaches towards -1, that means without any given input, some output is getting generated, and this condition is known as, so what happens? So under this condition, whenever this ASBS, this product is equal to -1, so that means even if you don't have any particular explicit input provided from the outside, so your AFS is equal to infinite or is very large. That means even if you don't have any explicit input provided from the outside, still you will be able to get some non-zero SO. Some non-zero SO you'll be able to get at some given frequency, not for all frequencies. Only for those frequencies at which this product ASBS or this LS is equal to -1. Only at those frequencies you can have that condition. You'll be having some SOS, non-zero SOS at some given frequencies, and this condition is known as the Barkhausen condition for oscillation. Barkhausen condition, so what is the, so if I consider this Barkhausen condition, so it is having two different parameters. If L of S is equal to -1, that means what? The magnitude is equal to 1. If I consider this one, LS is equal to -1, that means what? The magnitude equal to 1, mod of LS is equal to 1, and what about the phase angle of this? Because as I have already told you that these both AS and BS, they will involve some frequency sensitive elements like capacitors, like inductors. So therefore, you expect that there will be some phase difference between the input and the output, right? And therefore, since L of S is equal to -1, so I can have mod of LS is equal to 1, and this angle of LS is equal to 180 degree. Angle of LS. That means whenever the signal traversing from this side to this side and through this BS, then what we find, there is a phase reversal of 180 degree. Right? Negative feedback. That means what? Say for example, I am having an input like this over here. I am having an input like this. Then this input is allowed to flow through this, then through this. Then once again when it comes back right at this point, then what do you expect? What do you expect? You expect that there is a loop gain of 1. That means if this magnitude, say for example, let it be, suppose this amplitude some v dash, say for example, right? Then whenever this signal is allowed to flow through this AS and BS, what is the loop gain? Loop gain is equal to LS, that is equal to AS BS, that is equal to -1. That means what? That means there is no change in the magnitude. There is no change in the magnitude, but there is a phase reversal by 180 degree. That means what? Whenever the signal reaches right at this point, whenever the signal reaches right at this point, what do you expect? You have the same signal, same magnitude with a phase reversal. That means what do you expect over here? You expect signal like this, where this difference is also v dashed, right? Okay, and then it is fed in the negative terminal. That means what? What about this S epsilon? This S epsilon is how much? S epsilon is equal to Si minus Sf. And remember, we have already told that this S of I is equal to 0. There is no explicit input from outside. So therefore, what is S of epsilon? That is equal to minus of S of f. Right? Okay, so what do you expect over here? This signal at the output of this BS, this is the same signal but 1 degree phase difference. Same magnitude but 1 degree phase difference. And what will be your S epsilon then? This is S of f. This magenta, this particular waveform, S of f. What is S of epsilon? Minus S of f. So what will be your new S of f? New S of epsilon. It is something like this, where this difference is equal to v dashed. So over and over, you find that the input at this particular feed network is having the same cell. There is no gain and there is no phase difference. So if we have the same input over here, you can expect the same output over there also. And that sets the fundamental idea of a sustained output. So you have got the same output over and over. Same output is obtained at the output, say SO. Same output is obtained in terms of their gain, and as long as this condition holds good, that LS is equal to -1, this LS is equal to -1, that condition might hold good for a single frequency, and that condition might hold good for a wide range of frequencies. Now, as long as this condition holds good, LS is equal to -1, then you can have some kind of same output. Same output is obtained at SO. Same output is obtained with no change in the magnitude, with no change in the frequency. That means there is no phase difference, there is no change in the magnitude. And we call this scenario as the generation of sustained output. Generation of sustained output. And since we have got this particular behavior without the presence of any explicit input, then this kind of circuit in electronics is known as an oscillator circuit, because what we have without applying any external input signal, even if your SI is equal to 0, you can have some sustained output at SO, sustained output with given frequency and given magnitude. Now, if the frequency is a singular frequency, if you have a single frequency for which this condition holds good, then what kind of wave shape do we expect at the output? Suppose this condition, this LS is equal to -1, this LS is equal to -1, this holds good for only a single frequency. Only a single frequency. Then what kind of output you can expect at SO? Might be, this condition might hold good for a single frequency, or it might hold good for a wide range of frequencies. Now, if it holds good for a single frequency, then obviously you can have a waveform at the output with a single frequency. Now, can you name any signal, any signal which comprises of a single frequency? Any signal? Can you name any signal which comprises of a single frequency? DC. DC comprises of zero frequency. It's not DC.
The signal key type.
What kind of signal? Is it a sinusoidal signal or exponential signal or sinusoidal? Why sinusoidal? Because a sinusoidal signal is the only signal available in the universe which consists of single frequency. No other signal in the universe you can find. A perfect sinusoidal wave is a signal which contains a single frequency. That's what is known as a monotone signal, single tone. Monotone signal, right? Single frequency. This condition holds good only, suppose this condition holds good for a single frequency. Then you can have a sinusoidal output over here. Over here you can have sinusoidal output. Right? So that is the basic idea behind the.
Sir, the square waveform, so can frequency change?
Obviously, the square waveform consists of almost all the frequencies. Ideal square wave. If I have ideal square wave, I don't know whether you have studied ideal square wave, something like this. Have you studied the Fourier series?
Fourier series.
You studied now Fourier series? So this goes like this, minus to plus infinity. Have you studied Fourier series? A periodic waveform can be represented as a summation of different sinusoidal frequencies, sinusoidal signals of varying frequency and amplitude. If you know this particular formula, f of t is how much? Some a0 plus summation n going from 1 to infinity n sin of n omega 0, this one. You will understand, you will study this in the depth of these different types of signals, their representation in the sinusoid, their representation in the time domain, their representation in the frequency domain, in much more depth in the next semester, right? But this, what I can tell you right at this moment, and whenever you have a square wave like this, that means it involves so many sinusoidal signals, ideally infinite number of sinusoidal signals, ideally infinite number of sinusoidal signals of varying frequencies. So that ultimately you can generate this sinusoidal, this square wave signal. But sinusoidal signal is the only signal available in the universe which comprises of a single frequency. Now, hopefully, this amplifier circuit is well known to you. This part, I'm just marking this part. Well known, yes or no?
Yes.
What kind of amplifier it is? Common emitter amplifier with fixed bias.
Yes, sir.
Common emitter amplifier with fixed bypass capacitor is there. The effect of the bypass capacitor at signal frequency, you can expect that there is no. I mean, at signal frequency, you expect that this bypass capacitor effect is neglected, right? Now, this is your feed network. This is the feed network, right? Now, what do you know? You know that the output of the feed network is provided at the input of the back network. What is your back network here? So, the back network comprises of 3 stages of RC. This is one RC. This is another RC. This is third RC. CR, CR, CR dash. This is connected where? This is connected at the. So, let me just show you over here. This is the amplifier. This is the back network. I can draw like this. What else? Input of the back network is nothing but the output of the feed network, and here the output of the back is fed back to the input of the feed network like this. There is a negative sign. And there is no such explicit input present. There is no explicit input. And that is your final output. There is no input, but output is generated. Take a look at this one. This is the amplifier, right? This is the output node of the amplifier, collector terminal. This part is your back network, CR test, right? So output of the feed is provided at the input of the back. So output of the feed is provided to the input of the back. So this is the beginning of the back. So we observe. So this part is the back network. Let me show with a different color. Let me show with black. This is the back network, right? So this is the output of the feed. Is provided to the input of the back. One stage RC, second stage RC, third stage RC. Then this is the output of the back network. This is connected where? This is connected to the input of the feed network, right? So there is no such explicit input. You don't have any capacity, coupling capacity, you don't have any small signal present over here. This output of this back is given as the input of feed and vice versa.
Energy conservation equal to the
Yes, very good question. Very pertinent question. Very pertinent question. And how does you, how can you just simply say that the law of energy conservation holds good here? Law of energy conservation. Can anybody of you give me the answer? It's a very good question. There is no input, still the output is provided. Output is obtained. It's a very pertinent question, and I can tell you that in most of the grand value examinations, this is asked to the students. They can please explain that whether this energy conservation law is violated in the oscillator circuit design or not. Yes. Which one? B? VCC, yes. I have not provided any small signal. But the DC supply is there, no? DC supply is there, that is VCC. That supply you have provided, battery. That is there. Otherwise, the circuit will not be on. You have to ensure that, okay, this transistor is there in the active region, linear region. For which you have to provide some external biasing, external voltage. This is the supply voltage you have to provide. Right. So therefore, you can't expect that, okay, whenever I say no input, that means what? No external small signal is present. But the battery power supply is present, obviously present. Power supply is present. I don't know whether you have used these function generators. Have you used function generators? Yes, you have used the function generators in your lab. So until unless you just switch on this function generator, right? Until unless you plug in this one, can you expect any output? No. So that supply has to provide it. Until unless you have the supply, then how can you expect that this will generate something? Okay. So now, yes. And remember the last stage, if I consider this one, if you closely observe, this is CR, and this one is not CR, rather CR test. Why? Because ultimately, you understand that this is connected to the input, the base of the transistor. And in the base of the transistor, apart from your R dash, there are other resistors also between this point and AC ground. What are those resistors which are connected or which are present between this base terminal and the ground? Apart from this R test, what we expect? Base and ground, this point and ground. From this point to ground, what is the resistance? This one R, this one R. From here to ground, you have this R dash. Apart from that, any other resistors? You have R pi, base to emitter. Base to emitter you have R pi, emitter is grounded because REC combination, emitter is grounded basically. So R pi is there from base to ground and RB is there between base to ground. So we have to select R dash in such a way so that R dash, RB, R pi, their parallel combination will give you R. Okay, this R pi, RB, R pi, RB, and so R dash is has to be selected in such a fashion so that the parallel combination of RB, R pi, and R dash will give you R. Right. So ultimately, this is a CR stage, this is a CR stage, this is also CR stage. Done? Okay. This one is very trivial. I mean, it's a well-known thing. It's from class 11, 12 physics. V1, Z1, Z2, voltage division, Z2 by Z1 plus Z2 V1. So, okay, why I have written over there? Because I will utilize this concept. So what is that voltage? This voltage is nothing but Z2 upon Z1 plus Z2 times V1. So I can also write it like 1 upon Z1, that means Y1 by Y1 plus Y2. Yes. So we will use this one, right? Because ultimately the circuit that we will deal is not that easy. So that's why we will use. Remember this one. What is this voltage? This voltage is nothing but the admittance of this divided by the summation of two admittances multiplied with this input voltage. We'll use this one. Okay. So now, what is that circuit? This part? What is this part? Can you remember? What is this? Feed network or back network? Back network. This is the input of the back network. What is that? VO, output voltage. And what is that? VO dashed. Because already we know what is the relation between the input and output of an amplifier. It's a common emitter amplifier. Common emitter amplifier with fixed bias, common emitter amplifier, emitter bypassed, emitter resistance bypass because you have bypass capacitor. So you already know that particular thing. So that part is well known to you, but this part is not well known to you. So let's have a look at this. Let's investigate this part once again. So input is V0 for back network and output is V0 dashed. So we are in the process of calculating the gain of this back network. What is the gain? V0 dashed by V0. Right? So this V0 dashed by V0. So there are intermediate stages like VA, VB, I can call it. This one is VA, this one is VB, this one is V0 dashed. So it is. No, it becomes R. This becomes R. Because whenever you connect, then R dash, RB, R pi, they are coming in parallel, and then ultimately it becomes R. Okay. So we need to calculate V0 dash by V0. We need to calculate V0 dash by V0, right? So for that, there are intermediate stages VA, VB. So accordingly, what is that? This is V0 dash by V0. So I can write like this. This is quite obvious. This is V0 dash by V0 is equal to V0 dashed by VB times VB by VA times VA by V0. Right? So V0 dashed by VB. What is that? V0 dashed this voltage by this voltage. Here you know this voltage is VB. Here you know this voltage is V0 dashed. What is the ratio of this by this? Admittance of this divided by the summation of these two admittances. This formula.
Oh, yes.
Yes, that's the.
What is admittance of C? SC. Impedance is 1 upon SC. The admittance is SC. SC upon the summation of two admittances. SC plus 1 by R. That is V0 dash by VB, which is simplified to SRC upon 1 plus SRC. Right? This is V0 dash by VB. It's not that easy when it comes to VB by VA. Why?
VB by VA.
VB by VA.
কারণ কি দুদিকেই সার্কিট আছে তো ইম্পিডেন্স টোটাল ইম্পিডেন্স গুলো আমাদের দুদিকেই নিতে হবে
Yes. So VB by VA, this admittance this admittance divided by this admittance plus this admittance. Now what is that? What is impedance? This part?
SC plus 1 by R.
They are in series. These two are in series. These two are in series. And this whole thing is in parallel with R. Right? So if they are in series, so what will be this? R and this one is 1 plus SC. R plus 1 by SC. R plus 1 by SC. This is so this is the equivalent impedance. Right?
1 by R.
1 by this is nothing but the equivalent admittance. Plus 1 by R, the admittance is added, simply added if they are in parallel. So 1 by R plus 1 by this. So this part is basically the admittance of this whole thing. Right? So this admittance plus the admittance of this will be there in the denominator, and the numerator you have the admittance of this. Okay? Then if you simply go for simplification for this one, then what you get is this SRC into 1 plus SRC upon 1 plus 3 SRC plus SRC whole square. Right? Now the final one. That means VA upon V naught. Now this time let's assume that this so for better understanding I have used from different name R1, R2, R3. I ultimately this R1, R2, R3 they are same, C1, C2, C3 they are same, but to make you understand the thing, so I have used this one. What is the concept? VA upon V naught. What is that? This admittance divided by this admittance plus this whole admittance. So in the numerator you have simply SC, and suppose this admittance is Y1, looking at this. So what is that Y1? What is that Y1? Try to understand. R3, C3 they are in series. So R3 plus 1 by SC3 impedance. 1 by this is the admittance. This is coming in parallel with R2. So 1 by R2 plus this. This is the overall admittance. This is the overall admittance. Right? So what is overall impedance? 1 by this. Overall impedance. This is coming in series with C2. So what is the impedance from here to here? 1 by SC2 plus this. That is the overall impedance. Right? What is the admittance? 1 by this. This is coming in parallel with R1. So 1 by R1 plus this entire thing. Now, we know R1 equal to R2 is equal to R3 is equal to R, C1, C2, C3 equal to C. If I simply substitute this one, what I get? SC1 by SC1 plus Y1. This expression SRC into 1 plus 3 SRC into S square R square C square upon 1 plus 5 SRC plus 6 S square R square C square plus SQ RQ CQ. That's a big expression. Thankfully, when you multiply, this 1 plus 3 SRC plus SRC whole square gets cancelled. That is there in the denominator in VB by V expression, and in VA upon V naught expression that is there in the numerator. So already we have computed these three different factors: V naught dash by VB, V naught dash by VB the most simplest one, SRC 1 plus SRC, VB upon VA moderately complicated one, and then finally VA upon V naught, the most complicated expression. What is feedback factor VS? V naught dash by V naught? Product of these three. What is that product? We simply plug in the values. you have SRC, one SRC, second SRC, third SRC. SRC whole cube, right? And 1 plus SRC, here 1 plus SRC here gets cancelled. 1 plus 3 SRC plus SRC whole square, 1 plus 3 SRC plus SRC whole square gets cancelled. So, in the expression of BS, you have SRC whole cube upon this entire thing. 6 s square r square c square plus s cube r cube c cube. That is the expression for BS. And S is the complex frequency, as you know. It is having the sigma part and omega part. We are interested in observing the omega part. S is equal to sigma plus j omega. What will be the j omega? What is the value of this B of j omega? You know that S is equal to sigma plus j omega. Typically, you should write capital omega. It should be j plus capital omega. That is the analog omega, and this small omega is the digital omega. So here we have used digital omega, small omega. Anyway, typically you should write capital omega.
Digital omega?
The digital frequency. This is analog frequency. You will understand the difference between the analog frequency and the digital frequency in the subsequent semester, subsequent courses. This one not the same. Anyway, as far as our notation goes, this one we call it as analog frequency, and this small one we call it as the digital frequency. Anyway, so here we use the small omega as the analog frequency, that is equal to j of omega, right? So if you simply put S is equal to j of omega, then what is B of j omega? This B of j omega is this much. J is equal to square root of minus 1. What do you get? B j omega is equal to minus j omega cube r cube c cube upon this entire expression. Now you know you have the condition that has to be satisfied is that the loop gain Ls is equal to minus 1. Ls is equal to minus 1. Right. What is this B? B of j omega that you have got like minus this entire thing. Right. So, in order to ensure that there is no phase reversal, already the amplifier itself provides some 180 phase difference from its base to emitter, base to collector. From base to collector, there is a 180 phase difference. What I have told you at the very beginning, that whenever the signal is traversing through this loop, this AS, BS is equal to, in some of the books you will find that the loop gain, in some of the books you will find that the loop gain is equal to unity with no phase difference. That means what? That means the phase difference provided by the amplifier is another 180 degree. If you take into account this one, then there is no phase difference. So if I implicitly, so there is a misconfusion that in some of the books you will find that the Barklausen condition states that there is no phase difference and the gain is equal to unity. In some of the books you will find that there is a phase difference of 180 degree. Right? So that misconception should not be there. The bottom line is that whenever the signal, so if I have this kind of thing like this, A here, B here, this is output. Whenever the signal is traversing like this, no? Initially signal starts from this particular point, gain and phase reversal through A, gain and phase reversal through B. Whenever it comes back over here, the first instance, the second instance, there is no phase reversal and there is no gain. So the signal which starts from this point like this in the first iteration, in the second iteration also the same signal is obtained with no phase difference, with no gain and no attenuation also. No phase difference, no gain, no attenuation. That means a replica. The signal which starts from this point gets amplified, phase reversal through A, gets attenuation, phase reversal through B, and then once again when it comes back over here, there is same thing, it's a replica. But in our case, we have assumed that LS is equal to -1. Why -1? Why there is a 1 degree phase difference? Because we know that implicitly the amplifier itself provides a 1 degree phase difference. So that's why -1. Because implicitly we assume that it's a negative feedback. So from here to here you understand that there is a negative part. So that's why we have considered that LS is equal to -1. Otherwise, if you just get rid of this one, then in that case the loop gain is equal to unity. Loop gain is equal to unity with no phase difference and with no gain, no attenuation. Unity gain, no phase difference. That is the concept. So already we know that this A of j omega in our case, since we have considered this common unit amplifier, so A of j omega is equal to 180 degree. So therefore, in order to ensure there is no phase reversal, this B of j omega has to be equal to 180 degree. So how can you ensure that this entire thing will provide you 180 degree phase difference? What is the condition? What is the condition? That this entire thing will give you 180 degree phase difference. You have -n outside, right? J there in the numerator. Denominator you have A plus JB in that particular form. You have to ensure that this entire thing must be, this entire thing apart from this minus sign, forget about the minus, this part what I expect, this part should be a real positive number. Because you have minus outside, so minus is equivalent to 1 degree. So this part should be real positive number. Right? So numerator you have some j into something, denominator you have a plus jb. So that has to be equal to 0. Right? Then jj gets cancelled, ultimately what you have minus something, minus some real part. Okay. So what is the condition? 1 minus 6 omega square r square c square is equal to 0. From where you get omega naught is equal to 1 by root 6 r. Clear? So for a given r and given c, is this omega naught constant? Is it a fixed value?
Yes.
Or range of values? Fixed value. So if r is given, say 1 kilo ohms, c is given, say 1 microfarad, then your omega naught is also constant. And this is known as, omega naught is known as the oscillation frequency, oscillation angular frequency. Right? The angular oscillation frequency is given by omega naught, and the corresponding Hertz frequency is given by 1 by twice by multiplied with omega naught. So that frequency is given by 1 by 2 pi root 6 Rc. That is the oscillation frequency in Hertz. And the angular oscillation frequency is given by 1 by root 6 Rc. Okay? Then we have satisfied one condition out of two of Barkhouse. That mod of A omega j omega equal to 1, and there is no phase reversal. Right? Actually, if I consider this one, I should not write it as 180. This should be 360. If I consider this A omega, B omega, I mean AJ omega, BJ omega, no phase difference. In that case, if I write 360 degree, that means there is no negative feedback assumed. So I can, so 180 degree if negative feedback is assumed. If not assumed, then 360 degree. If I assume that there is negative feedback, in that case, this will be only 180 degree because another 180 degree is coming from input to output of AJ omega. Can you get the point? If I consider this one, this is A, this is B, this is the output. So when the signal is traversing through this, we expect that there is no phase reversal, there is no gain, no attenuation. Now whenever I assume that, okay, there is a negative, I mean this input is applied in such a way that it is added in the negative phase, opposite phase. In that case, what do you expect? In that case, in the expression, you have A by 1 plus AB, A by 1 plus AB, so AB should be minus 1, so that the Barkhausen condition holds good. Now, if this condition is not, I mean, if this is not assumed internally, something like this, in that case, I don't know whether how is it added over there, how is it fed back. The only thing that I know is that from here to here, there is a 180 phase difference. From here to here. So you should expect that from here to here, there should be another 180 degree, so that the overall is 360. But if it is fed at the in opposite phase, if it is fed in the opposite phase, in that case, we should expect that from here to here, you require how much? 360. Here to here, you require 360. So it depends. Depending upon your observation, upon the what assumption you have made during the formation of this circuit. The only thing that you need to know is that when the signal is traversing, there should not be any gain, there should not be any attenuation, and there should not be any phase reversion. So we have obtained that this omega naught is equal to 1 upon root 6 RC, F naught is equal to 1 by 2 pi root 6 RC, and therefore, if you just simply plug in those values, then B is coming out to be, if you simply put this value, B is coming out to be minus 1 by 29. Minus 1 by 29. If you simply plug in that omega RC is equal to 1 by root 6, then B is coming out to be minus 1 by 29. That means this B network, this back network, provides an attenuation with value equal to 1 by 29 with a negative gain. That means there is a phase reversal and there is an attenuation. Can you get the point? There is a phase reversal and there is an attenuation. Then how to select the amplifier? What should be the gain of the amplifier? The gain of the amplifier should be 29. Mod of this amplifier, the mod gain should be called 29, so that the oscillation is sustained. Because the product should be 1, this B network is giving you a gain of minus 1 by 29. So this A network must provide a gain of 29 so that this AB product is equal to unity. Clear? Initially, to start with, initially you understand another question which might be asked by any one of you is that initially there was no such input. So initially, how can you expect that the oscillation is created at the beginning? At the beginning, if there is no such input, how can you expect that the oscillation starts all over? So initially, there is some noise, an external noise is there in the environment, and this noise is typically the noise is a wideband kind of noise. So noise is having a wide bandwidth. We call it a wideband noise. So this noise is initially provided at the input of the of this particular amplifier. The amplifier amplifies this particular thing, and what happens is this back network. What you have observed, this back network is giving a gain equal to minus 1 by 29 only at that particular frequency. What is that frequency? Omega hertz is equal to 1 by root 6. So for example, if I assume that R is equal to 1 kilo ohms and C is equal to, say, for example, 1 microfarad, then if you simply plug in those values, you will find out some oscillation frequency, some hertz, say some hertz frequency you'll be getting. So what about the behavior of this back network at some other frequencies? Of this particular back network at some other frequency. Only at this frequency, whenever omega hertz is equal to 1 by root 6, when omega hertz is equal to 1 by root 6, then only this j omega is equal to minus 1 by 29. And for other value, you will see that this is not equal to minus 1 by 29. So the Barkhausen condition gets satisfied only at this particular frequency. So initially, so whenever if you just switch on that oscillator circuit, initially it can capture the noise from the environment, and noise is having some wide band from, say, a few tens of hertz to, say, few hundreds of hertz, or even in the range of kilohertz or tens of kilohertz. Apart from that desired frequency of 1 by root 6 Rc, at some other frequencies, what happens? At the other frequencies, this Barkhausen condition is not satisfied. Therefore, since it is not satisfied, therefore you don't have any sustained output at the output of your feed network. Only at this particular frequency, 1 by root 6 Rc, you have the sustained output. So initially, to start with, what you can have, initially the gain can be made little bit higher than 29 to start the oscillation, and once the oscillation gets started, then you can select this mode of j omega is 29 to sustain the oscillation. Okay, and the selection of this value is very important. You have to make it very close to 29, right? Okay, it looks something like that. And this entire thing, this entire oscillator circuit that we have described so far is known as RC phase shift oscillator. And that is quite obvious as you observe or visualize the architecture of this particular back network. The back network, you have 3 RC networks, 3 RC circuits, 3 RC stages, stage 1, stage 2, stage 3. And overall phase shift is going to be 180 degree from input to output for back network. And individually, you have 3 stages. Each of these stages will provide you a phase shift of 60 degree. You can check it. You can check it that you have already calculated this one. You have already calculated this one. V0 by V0 dash by VB, VB by VA, and then VA by V0. So you have calculated. And if you just plug in that value, that omega hertz is equal to 1 by root 6, then you will see that each of these stages, V0 by VB, VA by VO, and VB by VA, each of them will provide a phase shift of phase shift equal to 60 degrees. Each stage provides a phase difference of 60 degrees. So from here to here you have 60 degree phase difference, from here to here you have another 60 degree phase difference, and from here to here you have another 60 degree phase difference. So all over from V0 to V0 dash you have 180 degree phase difference, right? V0 dash is provided where? test is
Input of the
input of the amplifier. So once again from V0 test, so you remember this is amplifier, right? What is amplifier output? VO, right? So from here to here 60 degree phase difference, here to here 60 degree, 60 degree. So from here to here 180. Amplifier itself provides a phase difference of 180, right? So whenever the signal starts from this point, 60 degree, 120 degree, 180 degree, and another 180 degree, comes back 0 degree, right?
স্যার আরেকটা যেটা আপনি বললেন না স্টার্টের সময় ওই নয়েজ নেয় তো নয়েজটাকে অ্যামপ্লিফাই করে তারপর
Noise gets amplified. Noise gets amplified, but if the remember that we have not discussed the frequency response characteristics of amplifier, but typically you understand that for any amplifier, the frequency response looks something like this. Typically, if this is your frequency axis and if this is your gain axis, it looks something like that. Now, if the noise remains within this range, from here to here, then the gain is like. Now, if the noise is very, if the frequency is very small or if it is very large, then the gain is relatively small and the corresponding gain is very small. So the amplifier output is typically very small. And then this output is fed back where? This output is fed back at the input of your back network. And remember, this back network provides some output which is a function of frequency itself. And this output is maximum. This output is maximum whenever, or with. This will be. This will give you 180 degree phase difference. If I once again consider this product, yeah, this one. This is the system function or gain function for Bj. Only at omega RC is equal to 1 by root 6. Only at omega RC is equal to 1 by root 6, this Barkhausen condition gets satisfied. Otherwise, what do you expect? You expect that this Barkhausen condition is not satisfied. Not satisfied, that means what? You don't expect some sustained oscillation. So you can have some other frequencies. But only at this particular frequency, since it's a phase shift oscillator and this Barkhausen condition gets satisfied only for a single frequency, therefore you can have a single output, or rather a single frequency output. So this is one such oscillator circuit which involves R and C, known as RC phase shift oscillator. And second stage is something like that. So here what we have seen for phase shift oscillator, we have observed only one amplifier. One amplifier, and one RC network, right? So that's why this RC network has to produce a phase difference of 180 degree. Now, for some other circuit, you can have some RC network which can provide a phase difference is equal to 360 degree. In which case, you require two such CE amplifier, so that the overall phase difference is equal to 1 second 0 degree. Because as you understand, from here to here there is a 1 degree phase difference. From here to here you have an additional 1 degree phase difference, right? So from here to here the phase difference is equal to 0. So the back network doesn't provide any phase difference, 0 degree phase difference, right? And that can be achieved using a bridge circuit like this. You have 4 arms, R1C on there, studied bridge circuit. R2 C2 they are parallel, R1 C1 in series, R3 R4. Hmm? Yes, I'm coming to that. And this is the input to amplifier 1, and from these two nodes we are getting the output from the amplifier 2. It looks something like that. Two stages common emitter amplifier, two stage common emitter. First stage doesn't provide any local feedback, right? Second stage provide some feedback over there, back to the input of the bridge circuit. So what is your feedback factor then? What is feedback factor? Input to the amplifier 1 upon output of the amplifier 2, V0 dash upon VO2. So what is that? You can calculate this one. This one. Here what we have, this is the back network. This is the back network, right? The back network is receiving its input from the output of the amplifier 2, and it is feeding its output to the amplifier 1. This is the output of the back network, which is given to the input of amplifier 1. And from this two terminals, it is receiving the output from the amplifier 2 as its input. Okay. What is the formula? If it is V0 dash, VO2, suppose this is ZS, it is ZP. What is the formula then? ZP you have to identify. You can identify ZS and ZP. Yes or no? What is ZS from this circuit? This is V02, VO2. This is ground, right? Then, what is VO dash? What is VO dash? Basically, the voltage at, yes or no? So therefore, this is ZS. This is ZP. Now try to identify VO2, ZS, ZS. This terminal is your output terminal, V0 dash. Through VP, through ZP, it's connected to ground. Okay? You calculate what is ZS? 1 plus SRC upon SC. What is ZP? R by 1 plus SRC. Right? What is the feedback factor then? VO dash by VO2. VO dash is the output of your feedback network or back network, and VO2 is the input of the back network. So their ratio V0 dash upon VO2, VO dash upon VO2 will give you the feedback factor. What is that? ZP upon ZS plus ZP. Right? What is that? If you simply plug in those values, substitute those values, then what you are getting this one. SRC upon 1 plus 3 SRC plus SRC whole square. That is J omega RC upon 1 minus omega square R square C square plus J into 3 omega RC. This time what do we expect? We should expect that this B of S, this B of S or B of J omega must be equal to unity. As far as the gain is concerned, that is unity, and as far as their phase shift is concerned, that should be 0 degree. Right? Because already you have these two stages. This stage 180 degree, this stage additional 180 degree. So from here to here, no phase difference. Right? From here to here, 180 degree, from here to here 180 degree, from here to here additional 180 degree. So from here to here, no phase difference. So therefore, this particular back network must not provide any additional phase difference. So that whenever the signal is traversing through the loop, 0 degree phase difference. So what is the condition? You have J omega RC, the numerator, 1 minus omega square C square plus J into 3 omega RC. The condition is the real part has to be equal to 0. So 1 minus omega square C square is equal to 0, which gives rise to omega naught is equal to 1 by RC. Right? 1 by RC. Okay? Now come to your question. Why should I use this one? You ask me at the very beginning, why should I go for this kind of, because we are happy with your this phase shift oscillator. So why should you go for this one? Remember that here, if I have some given value R and C, last time what we get, the expression for this omega naught, if I take a look, if you can remember, this was something like that, root 6 RC. So if I have some given R and given C, say R is equal to 1 kilo ohm, C is equal to 1 microfarad, then using that oscillator, phase shift oscillator, what you can have 1 by root 6 RC, that is oscillation frequency. Now sometimes for your application you need some higher oscillation frequency. It's not that all these your oscillators. So we'll study here in our syllabus we have 4 such oscillators. That is the second one. In fact, we have RC oscillators and we have LC oscillators. We will study 2 RC oscillators, that is 2 LC oscillators. Apart from that, we have the crystal oscillator. That is not there in our syllabus. We have the crystal oscillators also. So, what is the need of having so many oscillators? Because sometimes you require this oscillation. Sometimes the sinusoidal signal has to be generated at, say, kilohertz frequency. Sometimes it is required at tens of kilohertz frequency. Sometimes it is required at megahertz frequency. So therefore, depending upon the frequency of operations, the frequency of oscillation, you have to have different types of oscillator circuits. So if I just typically these RC oscillators typically they provide some. Their frequency oscillation typically small. And typically we start with the phase shift oscillator to begin our discussion. And as you understand, the corresponding angular oscillation frequency was obtained as 1 by root 6 RC. Sometimes you are not happy with this. 1 by root 6 is how much? How much? 2 point something. 2.5 or close to that. 2.5. Suppose you would like to, yes. Right? 2.6 is close to 2.5. 0.4. So sometimes you would like to have some higher oscillation frequency. So one option is that you go on increasing R and C. But that's not a good option, because if you go on increasing R and C, it is because if you increase the C value, then obviously it is having some other effects as far as their frequency response is concerned. So what you can do over there, so since this is 1 by root 6 Hz, sometimes with a given RNC, suppose you'd like to increase the your oscillation frequency. So that's why, okay, you go for this oscillator, which is known as the wine bridge oscillator. If you go for this oscillator, you will see that the corresponding oscillation frequency is given by 1 by RC. Obviously, it is more, no? Previously, it was 1 by 0.4 multiplied with, 0.4 times 1 by RC. This time it is only 1 by RC. So obviously the oscillation frequency is improved to some extent. If you move from your phase shift oscillator to the wine bridge oscillator, right? But still we are not happy, because with this kind of values, I mean, with typical RNC, this RC oscillator, they provide the oscillation frequency in the range of kilohertz, not more than that. So if you'd like to have some higher frequency value for getting those output, so therefore we have to move from RC oscillator to the LC oscillator. So we will study two oscillators. We have discussed two RC oscillators today. One is the phase shift oscillator, and the second one is the wine bridge oscillator. And then hopefully in the next class we will discuss two such LC oscillators. We have in our syllabus, we have two LC oscillators, namely the Hartley oscillator and the Colpitts oscillator. We will discuss two such oscillators, two such LC oscillators, and this is in our syllabus only. And apart from that, you have so many other oscillators like the crystal oscillator, and the other oscillators are also there, but that is not there in our syllabus. And if you go for the crystal oscillators, I would like to mention that the oscillation frequency, the signal that you will be getting out of these crystal oscillators, they are much more stable, and you can also generate some high frequency oscillation signal if you use those. Okay. So with this, let me conclude our today's discussion on oscillation.